Hello to my socially distanced general physics 105 class. Today we are learning about non-conservative forces. So the past few classes we've been discussing work and conservative forces. And so non-conservative forces are those that do not conserve mechanical energy. So primarily in this class we'll be considering friction, but there's other examples such as air resistance that would fall into this category as well. Now, when we do problems involving non-conservative forces, we have to treat them as external work. We cannot define a potential energy for friction. So, as I've said before, in your problem solving, you'll probably want to define your system as broadly as possible so that you can use potential energy for gravity and for the springs. But when there's friction involved, you're going to have to calculate the work done by friction, at least for this one. Now, the other thing about non-conservative forces is that non-conservative forces depend on the path taken. So we know that the potential energy, all that matters is where you start and where you end, and not the path that you take. But here, for non-conservative forces, it'll depend on how far you go. Right? So if you take a longer path from point A to point B, you're going to experience more friction along that way. So if we look at this example, just simple picture here of we have one person skiing and the other person trying to slide down the hill with shoes on grass. Now that may be possible if you've seen people try and in England try and chase wheels of cheese down a hill as they do for some sort of weird tradition. Definitely can get some sliding going on, but there's going to be a lot more friction and therefore a lot more energy lost from the system than there would be in the case of skis on snow, where the coefficient of friction would be very small. Now, we can calculate the work done by friction using our definition of friction, which is take the component of the force that's in the direction of the displacement, or in this case, opposite to the direction of the displacement, and multiply by the displacement. Now, you can see in my definition here for the work done by force, I've already gone ahead and put a negative sign, and we'll see why that's the case, that that the work done by friction is always negative. Now, if we are doing our free body diagrams and we want to figure out the force of friction, we do it just the same as always. So you can see um, in the next equation, I've just substituted instead of force of friction, I've put in the coefficient of kinetic friction times the normal force, which is just the way we've always been calculating the force of friction. Now, if we look at this block, which is about to slide on this horizontal table, if it slides to the right, the force of friction is going to be to the left, and of course it'll be kinetic friction. So as that happens, we can see the displacement is to the right, but the force of friction is to the left. So if the force of friction points to the left and the displacement is to the right, they point in opposite directions, and therefore the work done is always going to be negative. So that's always true for friction. The work done by friction is always negative, and it's always going to remove energy from the system. Okay, now we're going to take a look at an animated example. Will allow us to look at conservation of energy, and then also looking at a situation where we have to apply work once we introduce friction. So if we start with the skater at a certain height, so we can see looking at the bar graph that all of her energy is potential energy, so the potential energy bar graph matches the total. And as we drop her into the ramp, we can see that when she's at the bottom, the kinetic energy becomes a maximum, then it goes back to potential energy. Oh, and I dropped her from a little too high, so she flies off. All right, so let's start that again, maybe a little bit more cautiously, so we can see it going back and forth, and I'll go back to normal speed instead of slow motion. Okay, so we can see the kinetic and potential, in this case gravitational potential energy, flipping back and forth, and we can see the speed going from a 0 when it's at the highest point, when the kinetic energy is equal to 0, so 0 speed here, and becoming a maximum at the lowest point when all of the energy is kinetic energy. We can also look at just a ramp where you drop in and then go off to uh, straight line motion at the bottom. So we can see we start with all potential energy, and if we hit play, all that potential energy is going to become kinetic energy, and your speed just stays at that maximum value. Okay, but we know that this is only going to be true in idealized situations. So now let's go to a situation where we add in friction. So if we add in friction, so we'll start with like a medium mass and a medium coefficient of friction. Again, we'll look at the bar graph. Now, we know that throughout this, that friction is what we call a non-conservative force, meaning that it does not allow total mechanical energy to be conserved. Now, the way that this bar graph works is that, when you have friction, you're going to generate some heat, right? You can tell that by rubbing your hands together. The work done by friction there becomes the thermal energy or the heat that warms up your hands. So as we drop the skater in here, now instead of just going back and forth the same all the time, right, we still see kinetic energy increasing and then decreasing, potential energy going the other way, but the whole time we see this red bar creeping up. And that red bar creeping up is the work done by friction, which is now becoming thermal energy. So after a certain amount of time, and I'll let this go at normal speed now, normal playback speed, we can see that eventually all of that energy, it all started out as potential and is eventually going to become all thermal energy. We can also see this effect if we look at this kind of ramp where we start here with, again, all potential energy, but now watch the maximum speed when you get to the bottom. So before, once you got to the bottom, the speed stayed constant. But now we have friction continues to do work. Okay, so she's going off the screen, but she's continuing to slow down, right, wherever she is, off in the mountains somewhere, or the plains, the fields, whatever it is. But her speed is continuing to slow down. Her kinetic energy is continuing to decrease as friction does more and more work on her skateboard. Right, so we need to figure out, and in this case, we already know the definition of work. It's just going to be the force of friction times the displacement of the object. And the thing to remember about friction is that friction always does negative work. Right? Friction always slows you down. Friction always removes energy from the system. However you define your system, work done by friction will always remove energy. Uh, Demo that reminds us a bit about centripetal motion using the freeform version, and that allows us to make the track whatever we want. So here we can look at the skater starting up here. It's higher than the top of the loop, so we might expect, well, whatever potential energy she has here is going to be greater than at the top of the loop, so she'll definitely have some kinetic energy and still be moving as she goes around. But as we watch this go in slow motion, right, so we can see the potential energy decreases as it gets to the bottom, greatest kinetic energy at the bottom, but then near the top, she flies off, right, and okay, she magically gets back on, but if that were a roller coaster, that would be really dangerous. Now we can see that just having some kinetic energy at the top of the loop is not enough. We need to have a situation where that velocity matches the centripetal acceleration that's required to go around the loop. So if we make the loop, we keep the top at the same height, but we make the loop a little bit tighter, right? So now we have a smaller radius. Now the centripetal acceleration should be high enough to allow her to go smoothly around the loop. Let's watch. All right, so here she makes it all the way around without losing contact. So this is a reminder that we, even as we think about kinetic energy, for certain situations, we still have to remember centripetal motion. Right, so here's some multiple choice questions to try and test your understanding. For all of these, you should think about defining the energy at the start and looking at the energy at the end and seeing how much of that energy of the system is lost to friction. So here we have a block sliding down a frictionless ramp of height h. It then experiences friction in the horizontal portion, coming to rest after traveling a distance capital D. So you can see that the sort of shiny metallic part is supposed to be frictionless, and then when we see the sort of sandy or rocky picture, that's where the friction is being experienced. Okay, so if we started from a smaller hill, think about what that would do to the initial energy of the block. Is it going to have more energy or less energy? Okay, so then whatever energy you start with, all that energy is going to be lost to friction, right? Because at the beginning you have some potential energy, maybe have some kinetic energy, but at the end, the gravitational potential energy has gone to zero when you're at a height of zero, and the kinetic energy is going to zero when it comes to rest. Okay, so if we made the height of the hill smaller, what would happen to the distance the block travels? Will it be the same distance d? Will it be less than d? Will it be greater than d? Or is there more information needed? Right, and you can answer in the pop-up that's coming up on the Vizia video. Okay, so the answer is going to be less than d, right? And we can see the reason for that. If we start from a lower height, then we have less energy to start with. So therefore, as we go from the starting energy to the ending energy, that's a smaller change. And so there's less work done that needs to be done by friction to bring the block to rest. Now, the force of friction is going to be the same no matter what. So the only way that we can make the work done by friction less is to have it go a smaller distance. All right, let's try another example. So how about here? If we have the same situation, but rather than changing the height, we make the mass of the block bigger. What will happen to the distance the block travels before stopping? Will it be equal to d, less than d, greater than d, or is more information needed? All right, this one's a little tricky. It's going to be the same distance. Because if we think about, okay, the energy that we start with is going to be greater because of the greater mass. So we need more work done by friction. But we automatically get a bigger force of friction when we have a bigger mass, right? As the mass increases, then the normal force is going to have to increase, and therefore we get a greater force of friction. So because both of those depend on mass, the starting energy and the force of friction, and therefore the work done by friction, it's going to travel the same distance. Let's look at this example a little bit more in depth mathematically. So the first thing that we want to do in any energy problem is define our 2 points. So our first point, point 1, is going to be at when the block is moving at the top of the ramp. So we're going to define our potential energy to be 0, or we can alternatively say our height is equal to 0 when the block is at its lowest point. So if we look at point 1, we're going to have some gravitational potential energy, and we also have some kinetic energy since the block is already moving. So we can use our definitions for both of those. We can write the potential energy as mgh, and the kinetic energy is 1/2 mv squared. So we can see that the total energy there. Then at the end, when the block has reached the bottom and has moved through the part with friction and it has come to rest, as the problem said, then we could say, well, our potential energy is equal to 0 because our height is equal to 0, and our kinetic energy is equal to 0 because our block has come to rest, our velocity is equal to 0. So energy at point 2 is equal to 0. We don't have to worry about calculating at any intermediate points because we're not asked anything about that. We're just trying to look for the beginning and the end. Okay, so how can we relate those two? Well, we don't have energy conservation here, right? We're going to have external work due to friction. So what we have to do is write down that the external work is equal to the change in energy of the system. That change in energy is E2 minus E1, right? So we can write that down and bring those energies that we've already defined into those two places. So E2 is equal to 0, so we put that in front. And E1 is mgh plus 1/2 mv squared. So we put that there in parentheses. And we know that the external work is going to be the work done by friction, so I've labeled it W sub F now. Okay, so then we need to know what the work done by friction is. And as we said, the work done by friction is equal to negative force of friction times the displacement, which here is called capital D. So I'll use that letter to match the picture. And we know the force of friction is mu sub k times the normal force, so we make that substitution there. Now, in this case, because the normal force is completely balanced out by the force of gravity, we can say that the normal force is equal to the force of gravity, or mg. So we make that substitution. So we've got the work done by friction is equal to negative mu sub k times m times g times the displacement. So now we can set that expression equal to the one above. So the work done by friction there goes on the left, and then the change in energy expression goes on the right side. Then since we're trying to look at how the displacement changes, we can solve this for the displacement. Now we see every term has mass involved, so when we divide, that mass is going to cancel out. Both sides are negative, so we can cancel that out, and then we do our division there. So now, looking at this, we can answer both of our questions, which we answered conceptually. First, we can say, looking at the second question about how does the mass affect it? Well, mass doesn't show up in the calculation, so that means that it's going to travel the same distance for any given mass. And then we can also see that the height is in the top, so if the starting height were made smaller, which is what the question asked, then the displacement would become smaller as a result. Okay, here we have a slightly different situation where there's a dip in the frictionless part of the track before it comes back up to some intermediate height. And then there's some friction in the horizontal portion. Again, you can see in the color coding. So if we look at from point A to point B, what is happening to the kinetic energy of the block? So if it starts from rest and then it's given a little nudge and slides down, what's going to happen to the kinetic energy of the block? Is it increasing, decreasing, constant, or is more information needed? Okay, so hopefully you saw that so we can say that the gravitational potential energy is going to decrease. So in this portion, we don't have any friction, so the total energy stays the same. So as the gravitational potential energy decreases, the kinetic energy will increase. The block will speed up. Okay, now how about from point B to point C? In this case, the gravitational potential energy is increasing, so therefore the kinetic energy will have to decrease. All right, and then how about from point C to point D? In this case, it's moving horizontally, but there is friction. So in this portion, the gravitational potential energy stays the same, but there is work done on the system by friction. And because the work done on the system by friction is always negative, the total energy of the system is going to decrease. And because the gravitational potential energy is staying the same, the only way the total energy can decrease is if the kinetic energy decreases. Okay, so if we now let's look at total energy as we go from point A to point B. Now we have to define our system here. So here I'm telling you that you should consider the block and Earth together as a system, which means that you can consider the potential energy due to gravity. So as the block moves from point A to point B, what happens to the total energy of the block Earth system? That total energy is constant from A to B. Right? So the potential energy is decreasing, the kinetic energy is increasing, but those balance out, and there's no external work on the system. How about from B to C? The total energy is constant here as well. Again, no external work on the system. Finally, from C to D. Okay, hopefully you got here that at this point there is external work on the system due to friction, And so the total energy of the system would decrease because the work done by friction is always negative.